Welcome back, guys. In the last video, let me walk you through what we did last time. We were trying to build a model to predict the MPG rating for different vehicles in the Auto MPG dataset. So we imported the different libraries which we're using, the usual pandas and NumPy, Seaborn and Matplotlib for visualization. Then we imported Lasso cross-validation model from linear models. We're using standard scaling, we're using pipelines, model selection, we use train test plate. And for the metrics, we're looking at things like the mean absolute error, the R-square value, the mean square error, the mean absolute percentage error. So here what we just did is we imported the CSV file, look at the description of it, look at the head of the CSV. Then we drop certain columns that are not going to be useful, like car name and pretty much this column. We dropped it because it's just counting. So first thing, whenever you want to build a regression model for a particular feature, what you want to first see is what's the distribution of the targets. That's your Y feature, right? And that's what we did here. We can see that it's more heavy on the left-hand side, skewed more towards the left, and it has a long tail towards the right. For this, we just look at the basic. So for this, we're trying to build a very basic model. What we realize is displacement, horsepower, and weight. They all have a similar trend with the miles per gallon. So in a case like this, for linear models, you wouldn't want to just include them in there, because if you do that, what you're doing essentially is just adding redundant features. Okay, and now this is the acceleration. This is the model year, and this is the origin, whether it's from Europe, America, or Asia. So basic model, first select what our Y is, then we drop it, and we have our targets. We split into training and testing. Then we create a pipeline. So in the pipeline, what we're trying to say is any feature that comes in, first scale it using standard scaler, and then build the lasso regression on it. Of course, we fit and we see what our metrics are. So these are the metrics. They are not bad, but I know they can be better. And this is what it looks like. So the mean absolute error, so it means on average, the error of the prediction of the miles per gallon is going to be off by 2.5 units. And we want all these three to be as low as possible. We want this R squared to be as close to 1 as possible. And so this just shows the different weights that are put on it. For model 2, went ahead and dropped displacement and horsepower, because of course displacement, weight, and horsepower, if you check here, they all have the same trend. Okay, so the basic model was let's use everything. Model 2, what we are doing in model 2 is we are dropping those two. Now we can see that the R-square value actually increased. You can see from 0.79 to 0.8. So not a lot of increase, but definitely an increase nonetheless. And you can see there's some improvement. We have this here. So what we're going to do now is I've copied this file, so I'll save myself some typing. I'm going to engineer some new features. Okay, so let's go back to the top. So I pretty much copied everything. We'll do our imports, we'll do this, the usual things you do. So before we do exploratory analysis, let's try to engineer some features. Okay, so let's say feature engineering. Okay, and I have them somewhere here, so let's just copy them out and I explain what the logic is here. First feature we'll create is power to weight ratio. So for this, what we just do is take the power divided by the weight. Okay. Then displacement per cylinder. So we have information on the number of cylinders, we have information on displacement, and let me show you how they trend. So going here, we can see displacement as an inverse relationship with the MPG. Number of cylinder doesn't have any real relationship, so it has something like this, which is kind of weird. Let's go here and just instead merge both of them. So displacement is the total volume of an engine. So divide that total volume by number of cylinders, and that's how we get displacement per cylinder. Then power weight, it pretty much just multiplies the horsepower by the weight. Let me see if there are other features we can combine together. There could be. Well, if we do think of something, we can come back and add it. So let's just explore and see what the relationship is. So power weight ratio, power weight. So those are the three new features we've created. So power weight ratio, you can't see anything really striking there. So we're just going to skip on that and not use it in our features. Displacement per cylinder does have, some interesting correlations. So I'd say we add it. And here power times weight. So we just multiply power and weight. So what that means is we can go ahead and use this power weight instead. Okay, while we drop the power and the weight. And we can use this displacement per cylinder. So we can use these two features and drop the other features and then see how it's going to be. So acceleration, weight, horsepower, we can drop that. Okay, cool. Let's go ahead and, okay. So we can see the correlation of, let's say, displacement per cylinder minus 0.62. Let's see displacement alone 0.67, but let's see number of cylinders. Well, that really doesn't hold because we saw how it looked like. It looked kind of weird. So I believe there's a good balance between both of them. Power to weight ratio, not very strong. Power and weight multiplying each other. You can see it's combining those two features is actually better than those two features by themselves. Okay, you can see. One other thing we could do is, now since the reason why we might go this length is if you really must use like a linear regression. Another thing is we could look at this power weight and maybe look for the square root or something, because this does follow a curve, and for linear regression you are hoping they all follow a straight line, and of course that's definitely not the case in this case. If we use non-linear models or use something like a random forest, we should get some good results with this for sure. But let's see how far we can push our linear models. Let's see how far we can push it. That's the idea. Sometimes in real world, you're not able to use the most complicated model that you'd want to use. Sometimes it matters to the end user what the model is actually doing so they can trust it. And that's one thing you'd realize when you work in the real world. Okay. Enough of my rambling. So let's drop certain features. Let's just call this model 3. So I saved myself a lot of typing. Okay, model 3. We have our Y. We can drop this. So we've decided we're going to drop displacement and cylinder, because we're going to use this displacement per cylinder. So let's just copy that. Power weight. So we're dropping weight and power because we're going to use power weight. We're dropping cylinder and this because we're using cylinder. Power weight ratio, we could include it there, but it doesn't matter. We would allow the model to weed it out. Matter of fact, let's just remove it. We don't need it there at all. We do not need it there at all. Okay, so power weight ratio, model year, let's take it out as well. Yeah, even though there's some form of relationship, it's not because of the year itself, it's because technology has improved, and it won't be fair to include that in there. Okay, model year. Let's see. Displacement. Okay. Yeah, I think this is fine. So let's split it into our train and test. Okay. Do this. And let's make our predictions, and then, oh wow, it got even worse. Okay, it's bad. Wow. That's crazy. I was hoping these engineered features could have helped, but they didn't. That's weird. Okay, let's see. Previously for model 2, what did we do? Displacement and horsepower. Okay, we dropped those. Okay, cool. MPG. Well, we did drop a lot of features. The Part2 weight ratio, model year, displacement. Okay, let's do it again. We'll figure out what's going on here. So already you can see that linear models have their own limitation, because clearly when we look at the exploration here, we can see that it's not directly, like you can't say there's a direct linear relationship. You know, you can't say this is not linear. And so then it becomes a challenge, you know, definitely becomes a challenge. Okay, so let's not despair. So we did part weight ratio, we did displacement per cylinder. We could create another feature here. Displacement, cylinder, and acceleration. So let's see if, you know, and that's the whole idea, right? This is iterative. So you have to keep records of the models you had produced, and how they performed, things like that. Okay. Let's see. Not done this. Now it's definitely a bit worse. Let's see. Yeah, it's worse than just those two. Another thing we could do is we have displacement, horsepower, weight. We can just maybe combine all of them together, you know, but then you shouldn't expect the linear model to perform the best with that. So, but let's go ahead and do it. displacement, power, weight. So let's where was that? Okay, so let's multiply this by the displacement. Okay, let's see what it looks like. Displacement, power, weight. So you can see now this is even more non-linear, right? You can see that. So this is a good feature, but it's not going to do well with the linear model because the linear model is trying to fit a straight line through them, right? But the good thing about it is we're able to include 1, 2, and 3 into one feature, and we're able to include displacement per cylinder into another feature, and we did some other bad features are not going to work. So just looking at this, I can tell you that the performance is going to be bad, because of course it's trying to build a linear model, and that's not the case, right? Trying to build a linear model, so already it's gonna be pretty bad, but let's see. So let's see the weight that's being placed here on the different features. So it puts a high relationship on power weight, and you put something lower on displacement power weight. So let's go take out this power weight, because essentially this information is available here as well, and that might help. The origin, well, it does have something strong, at least better than the acceleration. Displacement per cylinder. So let's go take out this displacement, cylinder, acceleration, take it out, and let's take out this power weight. Okay, so let's drop this. The reason why is displacement power weight already has this information, so we don't need that. Let's see, what was the other one? Displacement per cylinder, acceleration wasn't a very great feature to begin with. We can take it out. Okay. Okay. Oh, my bad. We need to run all from above. Okay, let's see. Yeah, so it's a bit worse. Okay, so that didn't help. Essentially we created some nice, interesting features. However, because we're trying to use a linear model, that's why we have this issue. So what I'm going to do now is I'm going to go ahead and this is going to be in the repo, so you can look at it. You can see, sometimes the amount of work you do to build a model So let me save this, and I'm just going to copy it and now use something like a random forest mode regressor. I will see the performance. So let me copy this. Rename it. Okay, so let's open that up. Now for us to use random forest, we need to import it from scikit-learn. So let's just do this from sklearn.ensemble. Okay, so that's what we have here. Let's import this usual stuff. So we engineered all these features. Power, displacement, power, weight, displacement per cylinder, acceleration. So let's first do a basic model. Okay, we've seen all of this. So we know we're not going to include cylinders because this is, just kind of weird. This is what the displacement looks like. Yes, a cylinder, horsepower, weight, with special relationship, model year, origin, displacement, weight ratio. No, so power, weight ratio, displacement per cylinder. I actually like this feature. Power, weight. So this is just multiplying both of them. Displacements. This looks like a whole mess. Displacement, power, weight. Okay. So when we did power, weight, this is what we had. When we did displacement times power times weight. So this accounts for all those three features. So we don't need to use them. Now you notice now we're trying to use a non-linear approach, right? So let's say this is model 4. Okay, so because we have displacement, power, weight, so we can drop displacement, power, weight. That makes sense to just drop this. We're using displacement per cylinder, so we can drop cylinder. We can drop power, weight ratio. That makes sense. Yeah, we can drop this. We can drop this. We can drop this as well. Okay, makes sense. So what do we have now? Let's look at the features. We have acceleration, origin, displacement per cylinder, displacement, power, weight. So we have, so let's use something. Let's change this to random forest. Random forest. Yeah. Just copy that. Yeah, I changed my keyboard and the shortcuts are not working on this new keyboard. This is ridiculous. Okay. All right. So let's go in here. Number of estimators, the criterion, yada, yada, yada. Let me do this in a way that it's going to be more, easily readable. Put that in the next line. Then I can specify some of these things. Usually I just like to copy this. Okay, yeah, that's a bit too long, but we'll leave it like that. Okay. Well. Okay. Not looking too bad, looking too shabby, but I know I've gotten better before, so not like I'm excited. Okay, yeah, this doesn't have this, so this doesn't count any longer. Okay, so this is model 4. Let's go ahead and just do model 5. Okay. Okay, so what I'm gonna do is I'm gonna run, just the basic model here, but with a more powerful model. Okay, so let's do that. All right, let's do that. So instead of doing this in place, I could just, let's say df5 equals to df dot. Okay, cool. All right, let me run all of them above. Run all above selected cells. Yeah. Just pass all the features through there and see. So this is what I'm doing. Let me copy this. So let's say train 5, so that way we can distinguish. Okay, let's do that. So we have our pipeline set up. Okay. Okay, let me say pipe 5. Oops. That way we are sure we are doing something different, which really doesn't really matter. But so let's do this. See, I'm copying a lot here. Let me just do this. So say pipe 5. Okay, we have that. Now we can make our prediction. Let's call it prediction 5. Just so it's different. 5, 5, 5. Cool. This is put underscore 5 here. So let's do this. Yeah, let's print it out. Okay, 8.5. Let's see. Better than the basic model we had previously. So let's see. Yeah, 8.5. Okay, so let's print the mean average error. .98. Slightly, better than usual. Slightly better than usual. Okay, let's print. Mean squared error, then let's do this as well. Okay, it's getting better. So what we did here was we went ahead and built it using just all the basic features. Now what we could do, we could go ahead and that's included the feature engineered features. We could go ahead, let's change this to model 6. Okay, our y is the same. We can decide, okay, this wants to be 6 equals to, so we drop, so let's not drop any of these. Let's not drop any of that. So what we could do is, I want us to drop all the engineered features. So all of this. Sorry. Let's drop all the engineered features. Now this is just a very basic approach. Let me delete all of this. Power weight ratio, do we have that somewhere? We have it there. So let's not drop it twice. Okay, cool. So essentially what we're doing is we're not using any of the engineered features. We're just going to use all the features as is. Okay, let's see df6, the columns. Oh, my bad. Think. So let's run all above. Doing any feature engineering here. Let's see what the result is going to be. I remember all of this is being done live. I take a data set and I just add them live, so. Okay, let's just say pipe 6, just so we don't make any mistakes. 6 feet, 6. So this is 6. Sure I did the right thing previously. 555, cool. PG. Okay, let's do this again. This is for model 6. You have to take off the MPG. So here for model 5 is still the best model we have so far. So how about we do this? For model 5, let's look at, okay, let's do model 7 this time around. Okay, so we already have our engineered features. Let's look at the 7th model. Okay, let's say model 7. Now in this case, what we're going to do, model 7, let's change this to markdown. Yes. For this, what we want is, let's look at this. Okay, so because we can, let's pick this feature. Essentially we'll just pick this feature because it's essentially a combination of this, this, and this. I can do displacements per cylinder as well. So we are doing this and this. We can include origin, acceleration. I will build a model with that. Okay, so let's go ahead and do that. Cylinder. Okay, before we do that, let's get our Y. We already have Y everywhere, so that's fine. Displacement per weight. Okay, so df7 is equals to df displacement, power, and weight. Okay. So let's look at displacement per cylinder. A different feature. You can also look at origin. Origin, okay. You can look at acceleration. One, two, three, four. So we're using these 4 features. Let's see. Oh. Okay. Let's see origins. Okay. Cool. Let's just run everything above. Run this, run all above selected cell. Okay, so what's the problem? Okay, key error. So those keys are not there. So let's see. It's possible. Okay, that's why the mistake was. It's missing a square bracket there, so let's just do this. We can change this to 7. Okay, we have that, so let's just do essentially the same thing here. Let's give it a different name. Okay, and let's fit it. Okay, so this should fit on 7 and 7. Okay, let's look at the prediction. So 7. So we can change all of these. Okay, let's print 71. It's not the best I've seen. Because even with the basic model, it's 79, essentially 80. So model 7 is not looking good already. Nah, it's not looking good. Nope, nope, nope. Okay, so far so good. The best model we've had was one where we engineered new features and we just included those features here, right? And this essentially is the best model we've had. Okay, this is the best model we've had so far. Strange, but yeah, that's it. So with this, the feature engineering definitely helped. And so because this is a random forest model, it didn't have an issue with us passing in all the features in there, whether they are correlated or not correlated. Because with linear models, you have to make sure that you're not passing 2 features that are highly correlated with each other, because then it's not going to work. And that's why for the linear models approach, I ended up using the Lasso regression model, because that by itself takes care of that problem. Okay, so I engineered all these features. I was really wishing and hoping we could get to like an R-square of 0.9. You know, that's what I was really hoping we could get to. But that didn't work out. Another feature we could look at is power to acceleration ratio. You know, the more power you have, the more acceleration you could have. Let's see. How do I put this, looking at it from a physics standpoint. If you divide your force divided by mass, that's what will give you the acceleration. I'm trying to think of an intelligent way of incorporating, the acceleration and the power together. We could just look at maybe power to acceleration ratio. Let's look at that. So that's the idea with feature engineering. You just, keep creating features, and you just, you see what works, essentially. See what works. Ration power ratio. Okay. So that's what it's going to be. Let me copy this set up, type it. Okay, so let's just see how it relates. It's going to be the last one here. Acceleration power ratio. You can see that's a much better relationship than just acceleration itself. So when you look at acceleration itself, it's all over the place. But you look at this ratio, you can see that there's a kind of linear relationship, although there are some points that are being bad all over the place. So anyways, I'll be more than happy to include it in here. So model 5, which is as of right now our best model. Let's see. Well, slight improvement. In terms of the R square, let's say a slight improvement. Let me include it here. Slight improvement. I believe this one, so we have the engineered features, the origin as well, acceleration power ratio. You could look at, we could just add, I believe we have the power weight ratio here. Did I have displacement per cylinder here? Displacement per cylinder, power weight. So let me see if we have power weight ratio. Okay, let's see. Power weight ratio. Maybe we can add that in here. Made it even worse. Okay, can just take it out. So as of right now, the best we've gotten so far with this model is 5, where we're able to get 8.6 or 8.7 in terms of feature. Yeah. So this is what it's looking like. So for right now, I actually believe that if this feature was included, this particular feature, if it's included in the base model, I believe the performance will be good. So let's just see. Let's see. I really want to try it out. So let's include it here. Just include it somewhere here. Okay, let me just run this from the beginning again. Okay, moment of truth we've all been waiting for. Okay, yeah, improved it slightly, you know. So now a question we can ask ourselves is this. When we look at, this feature here, we can see clearly this is in no way linear, right? I wonder if maybe it is something linear. So clearly this is not the way to go, because this isn't giving it the transformation I want. We can just do this, get back to where we were. So yeah, this is what the best model is looking like. For this, what we did was we first used random forest, and so this is the best model with random forest, and essentially we engineered all these features. Oh, thought I copied that out. Okay, let me just run all the cells. Sure. But one thing I'd want you to see is, even with a basic linear model, with the right type of linearish looking features, you might be able to still get good enough performance. So you can see here, we have R-square of 0.8, and this is with just a linear model. But of course, the reason why we're having, not as good a performance here is because when you look at a lot of this, you can see that they have more of a curve kind of relationship, you can see. So if there's a way you can do it in such a way that they have like a linear relationship, then yes, you can still get good enough performance with a linear model. Okay, and now I'm even starting to think of yet another feature. Don't know if I want to do it because this video is already long, but you get the idea. Something like this that has like a linear look could be useful. Okay, so one last feature which I'll try just to try. So we have displacement power weight, these three multiplying each other. We can divide it by the acceleration and number of cylinders. Just now I'm really pretty much just cooking up features out of nowhere and see what sticks. And sometimes that's pretty much how it is, data science in the real world. Okay, let me just do this. So the idea is, of course, these three are multiplying each other, so it's more like a cubic quantity here. If we divide it by something like a squared quantity, we might get something linear, right? I don't know for sure. We can do the acceleration, and I have that somewhere. Yeah, cool. Times acceleration times the number of cylinders. Okay. Let's just say acceleration cylinders. Okay, let's see what that feature looks like here. Yeah, this is definitely not gonna help in the pursuit of something that is more linear, but it might be useful in a random forest scenario. Let's just see what it looks like here. Not really looking good there, but because we're using a random forest, it might be useful. So let's see. Hopefully we don't get something worse. This is the last iteration. Yeah, nothing too brilliant. So make me wonder if we should do it or not. So far, not too great. Okay, in that case, what we can do, we can go ahead and just take this out. We can go ahead and take this out. We don't need this. We can go ahead and take it out. We can go ahead and leave it in, but I'll just take it out. This is our attempt at creating new features. Let's run all cells. So far so good. This is the best performance so far. There's a course on Plotly Express which I just launched on Udemy. It's the most comprehensive course on Plotly Express because it covers lots of visuals on Plotly Express. Currently it's over 5 hours long. In this course you're going to learn how to create the different types of visuals we have here, and we're going to analyze a bunch of data sets. So you have chloroplates, scatter plots, violin plots, box plots, area plots, and we'll even cover animations. You're going to have lots of exercises where you can test your knowledge. The course is currently going on a discount for $12.99, but I also have 5 free coupons in the description below. Thank you very much, and let's continue with the lecture. Okay. Put that back in. Maybe include that feature back in. I'm not worried about it because yeah, so this is what it's looking like. Our score of 85. The mean average error is off by 1.9 most times. Mean squared error. So this is what it's looking like. We did have a model which had 0.86. But as of right now, I know I've included some crazy features here and there, and it's probably changed all of that. So, but that's fine. The idea is, yes, feature engineering is important. But start off with simple models like a linear model. Of course, you saw here that even with a linear model, we're able to get 0.8, which is fine, because good thing about this linear model is you can easily explain it to people. Like you can show them that, okay, so this is what the model is doing. It's looking at the acceleration power ratio. It's looking at the weight. It's looking at the acceleration, the model year and stuff like that. So it's included model year there, which, I mean, it's not the best thing to include in something like this, So of course, I'll definitely take that out of there, the model year, because it's not a useful feature. Okay. So but here, in terms of the origin, I don't really include the origin. So yeah, this is so far one of our best performing models. In a real life project, you'd want to stop at some point and not just keep on going. So but for right now, this is just to show you how to use pipelines, random forests, and how to carry out feature engineering. I may go ahead and build like a Streamlit. Web app based on this. Don't know, but we'll see. I may just do that. It won't be a big deal. But let's see. If I do that, I'll let you know and I'll upload it in the video as well. So thank you for watching, and I'll see you in the next video. Don't forget to follow me on Twitter and subscribe to this channel. Thank you.